Sorry, guys, for the delay. Yeah, I'll quickly cover the Velox IO optimizations. I know we're running out of time. So the main motivation for me to present this talk today is one, table scan, as we saw in Ori's talk and even in IBM, we are seeing it is the main top operator in the query performance, like it takes the most time. And the second factor is Velox IO is one of the least or has a sparse documentation. So there are a lot of, in fact, it's also the most complex. So I wanted to cover some of the concepts here, and hopefully I'll convert this into a doc next week. And the third reason is I meet a lot of storage optimizer, storage experts in IBM, and they all want to tinker the reads and the file system layer to sort of optimize the reads outside the Velox application. And I wanted to show you some of the optimizations you already have in Velox so that you don't sort of reinvent the wheel, and at least you know what's happening inside the application before you do outside at the file system layer. So it all starts with the table scan operator, right? So that's where most of the I/O is performed. And like I said, it has many layers, and I feel it's one of the most complex operators in the Velox library. You have the first layer is the Hive connector, and then you have the Hive data source, and then you have a split reader, and then inside the split reader you have a cached buffered input or the cache input stream, and then from there you have the file system reads, and then also you have the async data cache and you have the SSD cache. So you have all these components that are involved when you do any table scan operator. And I'll quickly give you a high-level overview of some of these components I just mentioned. So again, at the execution level, right, you have the table scan operator, and then you have drivers. Depending on your execution model, the driver could be a thread or it could be a process if you're encapsulating at that level. So you have multiple drivers. Say in this example, you have aggregate and the table scan. So you have multiple pipelines and multiple drivers running the table scan operator. So that's one level of parallelism. And then each operator, right, it sort of, like I mentioned, it creates a Hive connector. And the Hive connector is responsible for the file format, like either you read the Hive Parquet or your dwarf file format. And then Parquet, again, is a columnar file format. So you have the schema, you have multiple row groups, and you have multiple column chunks within the Parquet file format. And then the split, as I mentioned, the split reader basically is a concept inside the table scan where it's a unit of processing. So the way you assign data to a table scan is in the form of splits, and you define a split by maybe for Parquet, it's sort of the file path followed by the offset and length. So that's how you define a split for the Hive connector for a Parquet file. And then the table scan, based on the filters and column selectors, tries to read only the data that is required. So it's not that you read the entire row group. It has some techniques inside the table scan to read only the data that is required. It uses statistics and whatnot based on the Hive data source to read the minimal data. So yeah, so at this level, the parallelism is at the driver level. So multiple drivers, you get multiple parallelism to read the files. Then the next, we have something called a split preload. This is sort of parallelism where I/O thread. So apart from the driver thread, we have a bunch of I/O threads that we instantiate at the Velox layer. And then as a driver is reading a split, it can preload other splits. So it'll read multiple splits and it'll assign some of the splits to a I/O thread to sort of prepare the data source. So the I/O threads will just read the file and make it ready for the driver to start processing. So that's sort of some asynchronous processing by that driver thread. So the default, so there's this max split preload driver that you can set to sort of preload how many ever splits you need per driver. And the default value is 2, and based on your needs, you can sort of disable it. So I think Meta internally disables it because they didn't see much benefit from doing preload because all of the data fits in the cache. But if you're in the lakehouse environment like the IBM's Watson X data, then you can't afford to fit all the data inside the async data cache. So you need to be able to maximize the I/O throughput in your lakehouse. Like I mentioned, they use separate I/O. The preload uses a separate I/O thread to prepare a split. So basically, essentially in the Parquet sense, it'll open the file, read the footer, and sort of be ready at the first row group to sort of start processing. And then if the IO threads are busy, say you have a limited IO thread, but you have so many drivers trying to enqueue into this queue, then the driver itself will continue to process that. So it's sort of a queue system where either the IO thread does it or the driver will pull it back and start processing the same. So you can see like this two threads then that will preload split 2 and split 3 while the driver is operating on split 1. Then the second, so one layer lower is the Parquet reader, right? So after once you open a file, the Parquet reader, it takes over and it starts processing the row groups. Here we have sort of another flag called row group prefetch, which tries to load multiple row groups into memory. So it doesn't read one row group column chunks, but it tries to read ahead into multiple row groups, and it'll try to load a couple of row groups based on this config. So it could be a single read or it could be multiple reads. It all depends on the lower layer, which is the buffered input, which I'll talk in the next slide. So buffered input basically handles all the reads. The Parquet reader just issues the reads, but it doesn't mean that the read actually happens at that stage. It all depends on the buffered input that is being used underneath on how the actual read gets processed. So there are two kinds of buffered input. One is the cache buffered input. When you enable the async data cache, it goes to the cache buffered input. And if you disable it, there's a direct buffered input, which is a different kind of buffered input. This is the path that's taken when you have the cache disabled. All right, so I'll focus on the cache buffered input because we all want to use the async data cache, and we want to sort of benefit from that as much as we can. So the cache buffered input does a bunch of things, right? So first it interacts with the async data cache and sees if the data is available in the cache and load from the cache instead of doing a file system IO. And then it'll see, it look into the SSD cache and see and checks there. And then also, all this is implemented by Ori. Ori is the expert in this. If you have any specific questions, you can ask him. So there's also this scan tracks access patterns. So if you see any input streams that are sort of or accessed frequently or they have affinity, then the access tracker, it sort of tracks all these patterns, and it can sort of prefetch streams smartly. So if you're loading one stream and if the access pattern sees that is also the other stream is also always accessed together, then it'll sort of prefetch the other stream, and it does some smart tricks there. I don't know exact metrics on exactly what are the metrics used here, but yeah, like I said, Ori knows more about this. And then once it sort of decides to read, there's something called coalescing. So if two reads are close to each other, then you can set a parameter to sort of load as a single read, but then you extract only the ranges that are required. So if you have a slow object store, then this is more beneficial. So you can do one read instead of doing multiple reads, which are slower. And there's some related Hive configs like the load quantum, max coalesce distance bytes, and max coalesce bytes that you can set. There's documentation for this that if you do for the exact semantics, but these are some of the configs that you can adjust to sort of tweak some of these behaviors. And there are also metrics, which I'll be covering in the next talk about how to track, like what are the reads, how many bytes are read, what is the latency that took to read this byte. So you can use all those metrics to sort of tune this further and optimize the IO. All right, so yeah, so and then after the cache buffered input, if it's not in the cache, if it has to do a read, then it'll sort of go use the file system instance to a client to sort of issue the read. We use the prereadv mostly for the read. So all file systems in Velox, like the GCS, S3 have an implementation of prereadv. Yeah, so essentially, there's a lot of tricks already in the Velox IO layer to maximize the IO throughput. So we haven't seen any significant gains by parallelizing any of the file system API calls. So in the past, I think some team at Intel tried to use a transfer manager for the S3 read, but they didn't see significant gains because already the many threads in the IO system that were saturating the bottleneck. In fact, it added more overhead because it was creating more curl clients and they were hitting some curl errors. So there's actually a performance degradation. And yeah, so this is the blog that Intel folks finally wrote after the evaluation. So they did some TPCH benchmark by tuning all these parameters that I was mentioned, and they made an analysis of what was the best they found for their data set. And then also there's this read benchmark that is there to sort of find out the throughput that Velox is actually seeing for your file system. So you can run this benchmark. It does a bunch of reads with different gaps and different values and read values, and then you'll see what throughput you can expect from your file system. But yeah, there's some documentation that needs to be added in the Velox, and we'll add that. But I think this is important for folks to sort of know before you implement more optimization on the file system layer. Yeah, that's pretty much my talk.